Okay, going to be working here on 13.6, which is parametric surfaces and their areas. So I'm going to be starting with 29. Find the equation of the plane that is tangent to the given surface at the specified point. So we have, they give us x equals u plus v, y equals 3u squared, and z equals u minus v, and the point they give us is 2, 3, 0. So we want to find the equation of a tangent plane. We need a point and we need a normal vector. So we have a point. To get the normal vector, remember this is really our vector function r of u v, written out in its parametric equations. So it's u plus v, 3u squared, u minus v. And then I'm going to need the partials. So partial r with respect to u is going to be 1, 6u, and 1. Partial of r with respect to v will be 1, 0, and negative 1. And then when we take the cross product of these two, that's how we'll get the normal vector we need. It'll be the vector, let's see, negative 6u. Coming up here, we get negative 1, which is positive 1. And then minus 1, but then plus, so plus 1. So that should be a 2. And then covering up, we get 0, and then negative 6u. Now, that's just our normal vector. What number am I doing? 29? Whoa. What the heck is this? Oh, 3, 6. I'm looking in the wrong section. Okay, so now let me try and figure out how I get to this point. So what u do I need? What does u need to be? And what does v need to be so that I'm at this point? Well, you can kind of get it from here. I know that the y coordinate, right? 3u squared must be 3, so u squared must be positive or negative 1. So, okay, that's one thing. How about this? 0 must be this, so u minus v must be 0. Well, I could have done it this way also. 2 here must be this, so u plus v must equal 2. That's a system of equations. I can do this one by elimination, just adding down. I get 2u must be 2, which means u must be 1. So u had to be 1. I narrowed it down better this way. And once I know what u is, I can get v. V is going to be, let's see, I know u is 1, so 1 plus v is 2, so v must be 1 also. So 1, 1. So now to get my normal vector, what I'll do is I will plug in 1 and 1 for u and v. So all I need is u. So negative 6, 2, and then negative 6. And now I can write the equation of the plane. So the equation of the plane will be negative 6, x minus x naught is 2, then plus 2, y minus 3, and then minus 6, and then z minus 0 equals 0. Let's just clean this up. Negative 6x plus 12 plus 2y minus 6 minus 6z equals 0. Negative 6x plus 2y minus 6z. Let's see, 12 take away 6 is going to be 6. Bring it to the other side, negative 6. I can reduce everything by a factor of 2. It's a negative right there. Okay. Yep, okay. All right, so I'll let you do 31 on your own. All right, let's look at number 33. Find the area of a surface. So the area of the plane that lies in the first octant. So this is a plane, and in the first octant, which is the one out here, it's going to cut through the plane. Let's see where this cuts through the xy plane. If we let z be 0, we get 3x plus 2y equals 6, which means 2y equals negative 3x plus 6, which means y equals negative 3 halves x plus 3. So if I'm looking at this in two-dimensional, this is x, this is y. I go up to 3 here, got a point down 3, 1, 2, 3 over 2, hits here at 2, here's 3. Right there, so something like that. So 1, 2 on my x-axis, 1, 2, 3 on my y-axis. This is where my plane cuts through, and it's like a tetrahedron. It actually hits up here at 6. You can get that by letting x and y be 0, z is 6. So we've got this like tetrahedron looking thing, and so we want the surface area of that. Well, we need to come up with some way of finding a parametric way of writing this, but we can use the fact that we can solve that for z up there. And now we know that z is some function of x and y. And we can use a special, the special formula, since the z coordinate is a function of x and y, I know that this is going to be the square root of 1 plus the partial of f with respect to x squared plus the partial of f with respect to y squared. That's going to be that magnitude of the cross product. And that's just equal to square root of, let's see, 1 plus partial f with respect to x is negative 3 squared is 9. With respect to y is negative 2 squared is 4. So this is just root 15. That's really nice. And so here's where I am. The surface area will be the double integral over d. D is the restriction on x and y that draw the surface. But because x and y are on the ground here, it's really the restriction that gives us this, all right? So my x's go from 0 to 2. My y's are between 0 and that line, but that line we already saw earlier was negative 3 halves x plus 3. But anyway, it's going to be the double integral over that of root 15 dA, which if I pull the root 15 out, I can do this really easily. It's root 15 double integral over d of 1 dA. And if I just know the area of that region, so this is a triangle. The height is 3, the base is 2, so the area of that is half of the base times height. That's 3. So area, right, is 3, so 3 root 15. This was 33. 3 root 14, what the heck? Area of D, 6. Where did my root 14? Oh, Robert. Okay, that's obvious. I don't even want to talk about it. 14. All right. How about number 35. Number 35, you have another plane that lies in a cylinder. So you've got this plane, x plus 2y plus 3z equals 1. It lies in the cylinder. Inside the cylinder, x squared plus y squared is 3. So let me just draw the plane real quick, if I could. If x and y are 0, z is 1/3. And if y and z are 0, x is 1. If, what am I doing? Y? X and z are 0, y is a half. Now, it's not talking about the first octant here, but just imagine this plane goes in every direction. And what I want to do is figure out the surface area, and we have a cylinder that cuts through this plane. Boy, that's really hard to see, but I have a plane. I've got the cylinder that comes through and cuts through, and when it cuts through this plane, I've got this surface here. So I want to know what that surface area is. Well, again, I can go up there and I can solve that for z. So move the x over, divide by 3, so negative 1/3 x. Move the y over, divide by 3. And then I had a 1 there. So that's the plane written as a function of x and y. And so I know that the partial of r with respect to x and then of y crossed magnitude is square root of 1 plus the partial of this with respect to x squared, which is negative 1/3 squared is 1/9, plus partial of this with respect to y, which is negative 2/3 squared is 4/9. See if I can add properly here. This is going to be 9/9 plus 1/9 plus 4/9, which is going to be square root of, let's see, 14/9, which is root 14 over 3. All right, so that's that part. Now, the region on the ground, I didn't talk about the region on the ground, D, but if we look at it, here's x, here's y. I knew it hit here at 1 and at 1/2 here. So I go down 1/2 over 1. So the slope is rise over run, so that's just negative 1/2. So the equation of this line is y equals negative 1/2 x plus 1/2. Right, that's this. Am I going to need that? Oh, wait, hold up. I take that back completely. Hold on, I screwed myself up here. I just used that to draw this and then said, you know, I need more of it. Actually, the region is going to be, I'm trying to draw the cylinder on the ground. I apologize. So let me not get ahead of myself here. I'm supposed to go double integral over d of this root 14 over 3 dA, which I can pull that out. So let me try and control this. Well, this is a perfect, if you look at the ground of that, on the ground in the xy plane, that's a perfect circle radius 3. So I'm going to go to polar here. And the polar restrictions I would have is theta is between 0 and 2 pi. And I need to go. R is between 0 and root 3. This is root 3 because that was 3. And so that double integral goes from 0 to 2 pi, goes from 0 to root 3. The root 14 over 3 comes out. R comes in because I went to polar, so let me just put R dr d theta. And I do need to leave, so let me just see if I can let it leave that there. I think that's a pretty straightforward integral. Just double check that what I've got is good. Oh, yeah, you know what? We could have just found the area over D, but this should come out to root 14 pi. Yeah. Yeah, when we were back right here, okay, I could pull the root 14 over 3 out, and then 1 dA, but what's the area of this region? Well, there's the region on the ground. The area of that is pi times the radius, root 3 squared, which is just 3 pi. And if I multiply that times this, the 3's cancel, and you just get the root 14 pi. I apologize I'm rushing through this, but I really just trying to get something out there for you. I've got more problems to do. I'll do those at another time. Okay, I'm picking up here, still working in 13.6, trying to find the area of the surface given by this equation in between this plane and this cylinder, parabolic cylinder. So three-dimensionally what we have is a cone. Okay, so I'll see what I can do here to draw this three-dimensionally. We have a cone like this, that's this. And then we have y equals x. Well, we know that on the ground, that's this dotted line, the diagonal. And if we look at it as a plane, it comes up, of course, and cuts through this cone. And then y equals x squared would look like this on the ground. And imagine that coming up and cutting through this also. So this is pretty difficult to see. Let's look at it from the top. If we look at it from the top, here's y equals x. And here's y equals x squared, like this. They hit each other here at 1. So imagine coming up straight out towards us, and there's actually a cone that starts here and goes down to the origin, and this is coming up and cutting through that cone, and so it creates this little sliver in here. It's going to be really hard for me to draw it, but you've got this little sliver on the inside here from where this region on the ground, actually they hit each other here. This region comes up and cuts through that cone, and we want to find the surface area of that little piece. All right, well, what we know is that we're going to have to find the double integral over d, right, of r of u cross r, partial of r with respect to v, dA. But the z that we have, right, the surface we have is actually written in terms of two variables. So z is in terms of x and y. So this is that special case. I know that z equals f of xy equals square root of x squared plus y squared. And therefore, the partial of r with respect to x crossed with partial of r with respect to y should be equal to the square root of 1 plus the partial of f with respect to x squared plus the partial of f with respect to y squared. So we've been using this formula. I think I'll keep this here. And that should be equal to, so that should be equal to square root of 1 plus, now it's going to get a little messy, the derivative of this with respect to x. So first of all, derivative of the square root of something, I'll do it right here, is 1 over 2 times the square root of the something. Then chain rule says times derivative of what's inside. Well, with respect to x, that's 2x. Respect to x here is 0, so you get 2x plus 0. So this is times 2x. The 2's cancel, and you just get x over root x squared plus y squared. So that's going to go right here, x over root x squared plus y squared. That's this. But then
squared. Then we take the derivative of f with respect to y. When we do that with respect to y, we get almost the same thing, except we'll have a y on top, and I'll let you just work through that on your own. Squared. And then when we actually go and square this, you get 1 plus, you square the top, you get x squared, you square the bottom, and the root goes away. Here you square the top, you get y squared, square the bottom, and the root goes away. And now what I'll do is I'll maybe get a common denominator. So I'll just rewrite this 1 over here as x squared plus y squared over x squared plus y squared, like that. Which now gives me square root of, let's see, x squared plus y squared plus x squared plus y squared. It's 2x squared plus 2y squared over the common denominator. And that's really nice because I can factor a 2 out of the top. So that'll become root 2x squared plus y squared over x squared plus y squared. The x squared plus y squareds cancel and you just get root 2. All right, so here's where I am. I need to find the double integral over the region D of root 2 dA. And I just need to find some way of representing my region D, which are the restrictions on x and y. Well, the restrictions on x and y come from this region in here, D, right? Because it was just where these two curves intersected the cone up here. So this is a type 1 region. It's going to go x from 0 to 1. And then the y value is bounded between, let's see, the bottom is x squared and the top is x. So we're ready. So we've got double integral 0 to 1 x squared to x of root 2 1 dA, like that. And you know what? Well, that area is not easy to find. I was going to say, if we were up here, we could have written root 2 double integral over d dA, and then if we could just find the area of this, we'd be done. But I don't know that area easily, so I can't. So I have to go through and just grind this thing out. Root 2 integral 0 to 1. Antiderivative of 1. Oh, I forgot to put dy dx here. Sorry. dy dx. Antiderivative of 1 with respect to y is just y. Evaluated x squared is y and x is y. Then dx. So this is root 2 integral 0 to 1. Replace y with x, we get x. Replace y with x squared, we get x squared. This is what we should have expected to see. And then antiderivative here is going to be 1/2 x squared. That's 1/3 x cubed. Evaluated 0 and 1. And if we plug in 1, we get 1/2 minus 1/3. If we plug in 0, we get 0. So this is just root 2 times, let's see, that's going to be 1/6. So root 2 over 6 should be our surface area. Double checking this real quick. Don't want to go too far and realize I made a little mistake. I've been prone to mistakes lately. I think it's the end of the semester. I'm just kind of spinning wheels here sometimes. What number was this? 36? Okay. we're good. All right, so let's see, what else do we want to look at? How about, I think 39 is pretty straightforward. Let's look at 40. So for 40, we want to find the area of the surface that's part of the paraboloid x equals y squared plus z squared that lies in the cylinder y squared plus z squared equals 9. All right, so the main point on this problem is to notice that these are not written in a way we'd like them to be. Like we'd like that to say z equals x squared plus y squared, something like that, or x squared plus y squared equals 9, because we're used to working with them that way. But we want to be comfortable going with orienting our surface a different direction. So this is going to open out the x-axis. So we have this this bowl that's coming out the x-axis, if that makes sense, right? It's paraboloid. And then we have a circle, right, that lives in the YZ plane with the free x variable. So, sorry, not a circle, a cylinder, which is coming out and punching through, right? So the circle starts here on the back, and then it comes through and it punches through our surface. And so what we want is the surface area of just that piece. Again, I can't do a great drawing of this, but if we look at it from the top, when I say top, what I mean is we're actually looking at it from this direction. We're looking down onto the YZ plane. X is coming out at us. Then our domain on the ground is this circle with radius 3, and then what we have is this bowl coming out towards us, right? And that bowl gets bigger as we go out, but we've cut it with this cylinder, so we're only looking from that bowl down to the origin here, and we're looking for that surface area. Well, this again falls into a special case because we can look at x as being a function of two variables, y and z. And it is exactly y squared plus z squared. So just like earlier we said z is a function of x and y, we're going to do the same thing. And then what we can do is we can do a shortcut on that cross product again, just like we had before, except it'll change a little bit. We're going to do the partial of r with respect to y, cross with partial of r with respect to z. This should be equal to the square root of 1 plus the partial of f with respect to y squared plus the partial of f with respect to z squared. So it's the same exact thing, except we're using y and z instead of x and y. And let's just look at what those are. This is going to be square root of 1 plus derivative of this with respect to y is 2y, but then I'm going to square it, so 4y squared, plus derivative of this with respect to z is 2z, but then I square it, so 4z squared. And I'm done with my cross. So I just need to find the double integral over the region D, which by the way is this thing, of square root of 1 plus 4x squared plus 4y squared dA. Well, when we look at this region D and we try and figure out how we're going to create our bounds, we realize, well, this is great for being polar. So if I go to polar coordinates, I know theta can go between 0 and 2 pi. I know my radius is going to be bounded between 0 and 3. And that convert this to polar. And I noticed that if I pull a 4 out of just these two, I get 4 times x squared plus y squared. And x squared plus y squared is r squared when we go to polar. So this new integral, when I switch it over, becomes double integral. I'll fill the limits in just a second. Square root of 1 plus 4r squared. Then I have to put in the r because I switched to polar. And then I'll say dr d theta. And then I'll put my limits. 0 to 3, 0 to 2 pi. So there's the integral, and I believe I've done one like that. I think I did it in class, I don't recall. But let me just give you what this answer is. You should get pi over 6 times 37 to the 3 halves minus 1. All right, so this would just be a basic u sub. Let this be u, the derivative of it's right here almost, and just work through the rest. So the main point of this problem was just to get you to see that if you have x in terms of two different variables, you can still use the same formula, it just changes up a little bit. All right, on the last problem I'm going to do, 42, this is really just to get you to finally see a problem where it is not a special case. Everything we've done up to this point has been a special case. And that's something like you have a helicoid, which is a spiral ramp. They have the vector equation of this spiral ramp as being u cosine v, u sine v, and v. And then they give you that u is between 0 and 1, and v is between 0 and, what are we going to? Pi. So this is going to draw a spiral ramp. So what we want to know is what the surface area of this is. Well, we're just going to go directly to our formulas here. We need to find the double integral over d of partial of r with respect to u cross partial of r with respect to v dA. That's what I need. So let me go figure out what all this is. All right, we've got partial of r with respect to u is equal to a vector. See, partial of this with respect to u is cosine v. Partial of this with respect to u is sine v. And partial of this with respect to u is 0. All right, the partial of r with respect to v will be, let's see, u is a constant, so negative u sine v, u cosine v, and 1. And now I need to find the cross product. So when I take the partial of r with respect to u and I cross it with the partial of r with respect to v, I get another vector. So let's see what this one looks like. Covering this up, sine v times 1 is sine v, u cosine v times 0 is 0, so just sine v. And then when I cover up the middle one, I'm going to do, let's see, cosine v, and this is 0, but remember it's the middle one, so I change the sign to negative cosine v. And now cover up this one. Cosine v times u cosine v is u cosine squared v. And then I do here to here, and I subtract, so it'll become plus u sine squared v. And notice that this right here, I can factor out a u, and then cosine squared v plus sine squared v is 1, so this is all just u. And finally, let me find the magnitude of this. So the magnitude of the partial of r with respect to u crossed with the partial of r with respect to v should be the square root of this squared, sine squared v, plus this squared. When you square a negative, it goes away, so cosine squared v, and then plus u, and that's really nice, because that's equal to square root of 1 plus u, Pythagorean identity. All right, so here's what I want to do. I want to integrate, u squared, pardon me, u squared. I want to integrate square root of 1 plus u squared. And I do have my limits of integration, and they're both between constants, so my order here doesn't matter. So I guess I'll go 0 to pi. Well, you know what? Yeah, 0 to pi, 0 to 1. d u d v. I'm just trying to figure out if I want to do a different order of integration. Let's Let's just stick with that. All right, so at this point we need to do this integral, and we have some options, all right? One option is to take a look at it and go, well, I remember from Cal 2, whenever I saw something like this, I would do this trig substitution and go through this whole process. But then you could also say, yeah, you know, there's some formulas in the back of the book for integrals, and specifically formula number 21 on reference page 6. So by formula number 21 in the back of the book, let's see, the outer integral stays. The antiderivative of this with respect to u, so I'm looking at this right here, that is going to be, it's u over 2, so exactly u over 2, square root of, now the formula says a squared plus u squared, but for us, this is a squared, which means a is 1. So it's just going to be 1 plus u squared, okay, plus the formula says a squared over 2, remember a is 1, so that's just 1/2, natural log of u plus square root of 1 plus u squared, and that's it. Okay, and then we evaluate that between 0 and 1. dv would come next. So let's plug in 1 for u and see what we get. So integral 0 to pi. Let's plug in 1. When we plug in 1, we get 1/2 square root of, let's see, 1 squared is 1, plus 1 is 2, so root 2, plus 1/2 natural log, let's see, 1 plus, again, root 2. And now minus, let's see what we get when we plug in 0. Plug in 0 here for u, kills this off because 0 over 2, it's all gone. And then right here, let's see what we get when we plug in 0. We get, I'll put it here, 1/2 natural log 0 plus square root of, let's see, that's 0 plus 1, that's square root of 1 is 1. But that's just a 1, natural log of 1 is 0, so this thing is gone. So that's it right there. dv, this is all gone. And that's all one big constant, right? So if this is all one big constant, I can pull that constant out, right? I have 1/2 root 2 plus 1/2 natural log of 1 plus root 2. That's all one big constant outside the integral 0 to pi of 1 dv. And when we do this integral, which I'll just do it real quick over here, it's v evaluated 0 to pi. All we get is pi. So the answer is going to be this times pi. So I'll just throw it right here, this times pi. And this was number 40. Crap, I forgot which one this was. 42? Yeah, 42. Okay. I think that should be enough to get you going on this, and I hope the videos I did here right now are a little better than the last ones that I did. For the earlier problems of this section, I was kind of in a hurry, so I apologize about that.